Good morning, physics. Today is Thursday, May 7th, and today we're going to be talking about applying wave behaviors. Now, with this, there is a few key factors of how we apply our wave behaviors. Number one being acoustics engineering, so designing things for how sounds work, and also sonar. So with this, what sort of happens is there's a few things. So with sonar, the idea is you have your ship, and let me sort of get to my image. So you have your ship. Your ship is going to send a pulse, sort of a pulse of sound down to the surface or down below it. It's sort of that big pong sound. I'm sure you've heard it a lot in a bunch of different movies. And so it sends a wave, and then the wave sort of hits the surface. And then what happens is the surface sort of sends a pulse back, reflecting the wave back to the ship. Now, what sort of happens, where it sort of gets interesting, is it's not just one point on the ship that is receiving the sound. It's multiple points. There's usually a bunch of different what are called hydrophones on the bottom of a ship to sort of record the ping back from the sonar. And the reason why they have it is because if it was just one point, the only thing you would really know, because of the way the waves travel, they sort of travel in an entire arc all around. So they'd be going even down over here, and if you just had one point, all you'd really get is sort of an idea of how close the closest thing was. If you end up having multiple points, you can sort of measure how long it takes for that wave to get back from various points. And using some pretty advanced math, you can actually have it calculated out with more accuracy depending on the number of hydrophones your vessel has. For the most part, you need at least 3 in order to triangulate any points. So in order to sort of have a map of the floor, you would need at least 3 hydrophones to really measure that. But beyond that, one of the things that sort of goes on is depending on the wavelength, you can get better and better detail. Because remember, the wavelength is sort of how big the waves are. So if you go with a really big wavelength, you have a sort of a mellow image. It interacts with things really easily, but you don't get a lot of that detail. So like you could see, instead of having an ocean floor that's pretty sort of rocky, to you, if you're using large wavelengths, it might just appear as sort of a pretty flat surface, rather than sort of this rocky, craggy part that you can sometimes see in some images. And what these boats are basically doing is they're using the fact that they have a pretty good sense of the speed of sound in the water. And so they're basically timing how long it takes for this wave to be released from the ship and then and then return to the various hydrophones that are sort of listening in and waiting for sound. And by doing that, they get the image, and some things can tend to interfere. So like not only do things like animals and various other critters can cause interference on the sonar, but also things like warm currents or cold currents, or any real currents in the water, or if there's, say, an output of a stream or something into the ocean, if you were trying to use sonar near that can cause issues, because right on the barrier, so like where they're expecting this one type of surface for how the sounds sort of go through, and if there's suddenly a different speed of sound caused by things like fresh water or colder than normal currents, then it sort of ends up making everything fuzzy because it's going to misinterpret, because the boat is sort of scheduled or programmed to expect a certain speed of sound, and when it hits that gap, the speed of sound changes, so then it's predicting an incorrect amount of distance going on, which can end up messing up sonar. So that's why it's sort of one of those things where it's an issue when you're sort of dealing with places where there's a lot of currents, and sonar isn't as accurate, And you can have some cases where if the speed of sound is moving much faster than you think it is, then it ends up sort of appearing as if the floor is closer than it is. Whereas if you have it much colder or slower, then you're going to sort of see the floor, the ocean floor, to be much farther away than it actually is, which can cause damage to hulls and such. So that's sort of the idea of what's going on today. Beyond this, we have our applying wave behaviors, which is Explore Explain 5. And it's fairly short. So like a little bit of it is sort of reading over how sonar is and answering some questions. And you can see some maps of sort of how sonar was being used to sort of map ocean floors. And you can get some pretty good details in some parts and less so in others. And then the last place that it's used is things with like acoustic engineering. Now, with acoustic engineering, one of the things that sort of happens is they find that hard surfaces, so like things that aren't porous, tend to reflect sound much easier. So this is sort of one of the reasons why when you say, like, put a blanket over your head and try to talk to your parent when you don't want to get up, it sort of comes out muffled and they can't really hear you. Because you have sort of an interlocking layer where there's air and material, and since it's constantly changing the speed of sound, since it has to like constantly change between solid object, air, solid object in order to get through, it doesn't really produce as much sound and sort of insulates it. And it's also why a lot of various orchestra halls, like in this, or various music venues, have this very sort of solid background to them, like a solid backing. So then they're able to reflect all that sound out forward and sort of have that idea of sort of more sound going in one direction rather than the sound going in all directions. Another thing is if you've ever seen the noise canceling foam, let me pull some up. So, with noise canceling foam, what sort of happens is you see these shapes. These shapes are, with this acoustic foam, like the way that they're shaped, they're meant to sort of trap the sound in between the peaks and then sort of absorb it with the foam. And it's sort of why they all look like that they belong in some sort of medieval torture device, is because it's sort of one of the best shapes in order to absorb the sound and sort of prevent it from being reflected back towards the where you produce the sound. And you end up with like huge, you can end up having walls of all of this. And the reason why they change it like that is so then by sort of flipping it back and forth, it makes it less likely for waves of a particular direction to be able to interfere or be able to be reflected than if they're all going the same way. And overall, it's just sort of like a cool property of noise canceling like things is that they're just sort of the idea of like, okay, we have this sound coming. Wow, what's the best way we can do to sort of redirect it so that it doesn't go back to the person that's making the sound? And two, what can we have that can sort of absorb the sound? And what we found is just similar to various like thermodynamic settings or thermodynamic ideas, is that layers of air between material is this really phenomenal insulator. And it's sort of like one of the reasons why fiberglass insulation is like such a big deal, because it's this layers of fibers with air trapped in between the layers. And so you end up with this thing that it just takes a lot of it's really hard for any energy to be able to pass through it. So yeah, just really cool things about sound. So this is pretty much it for today. What's going to happen tomorrow is we're going to go over, we're going to view some videos of people who have made various instruments or are making music using some unconventional methods. And what I'm going to ask of you all is to sort of describe how they're making this music or why the music is sort of hitting these certain notes and all of that. And I'll be going over some of that information as well tomorrow. So, have a good day.